Today we are learning how to obtain flash figures for uniaxial minerals. We use the flash figure to find a grain useful for characterizing minerals along their principal axes. In the first part of the video, I will explain the principal axes, and in the second part of the video, I will explain how to find a flash figure and use it. For uniaxial minerals, we label our principal axes as epsilon and omega. In uniaxial minerals, two axes are always equal to each other. These are always omega. In the microscope, we observe a slice of these ellipsoids. When a grain produces an optic axis-centered uniaxial interference figure, we are looking at a slice of the ellipsoid that is close to an omega-omega section. For uniaxial minerals, finding a flash figure lets us know that we are looking at a slice of the ellipsoid that looks down at an epsilon-omega section. It is important to note that epsilon and omega change depending on optic sign. In a uniaxial positive mineral, epsilon is the slow ray. In a uniaxial negative mineral, epsilon is the fast ray. Now, let's go through the steps to acquire a flash figure. Step 1. With the cross-polarizing filter in place, find a grain of a chosen mineral that exhibits particularly high retardation and interference colors. Step 2. Switch to the highest magnification and focus. Step 3. Switch on the Bertrand lens and the condensing lens. On this microscope model, the switch labeled BL above the cross-polarizer switch inserts both. Step 4. As you slowly rotate your stage, look for the flash figure. Your figure should become extinct from opposite corners and then illuminate itself in the other corners. Here, I am only rotating the stage by very little, only a couple of degrees. Now, let's try an example together and proceed to characterize the grain. In this thin section containing mostly one type of mineral, I find the grain that exhibits the highest retardation. I switch to the highest magnification, focus, and insert the condensing lens and the Bertrand lens. Rotating my stage by very little, I notice a flash figure. I now know that I have picked out a good grain for characterization along principal axes. Next, I take out my condensing lens and Bertrand lens and switch to a lower objective. Focusing on the same grain, I perform a fast and slow ray determination. Inserting my accessory plate from the southeast, I notice that in this direction, I am looking at the slow ray, and in this direction, I am looking at the fast ray. I figured out previously that this mineral is optically positive, which means that I am looking at omega in this direction and epsilon in this direction. Notice the orientation of epsilon and omega in an extinction position. Now I can take out my accessory plate and the cross polarizer and describe the mineral's color and relief in plain polarized light. We need to align our mineral grain such that epsilon is vibrating in the same direction as the lower polarizer. Here, the mineral is colorless with low relief. Now, I go back to cross-polarized light and align omega with the lower polarizer. In plain polarized light, I see that this mineral is colorless with low relief along omega. In this mineral, the difference between epsilon and omega is small and may be difficult to distinguish. Other minerals show much greater differences in color and relief between epsilon and omega. Here are some things to remember and some helpful tips. When picking out a grain to obtain a uniaxial flash figure, look for the grain exhibiting the highest retardation and interference colors. The flash figure lets us know that we picked a good grain for characterization along principal axes. Epsilon and omega change depending on optic sign. In a uniaxial positive mineral, epsilon is the slow ray. In a uniaxial negative mineral, epsilon is the fast ray.